Okay, so it's very strange to give a talk where the first slide says concluding remarks, right? So I was expecting that I will be terribly moved in the moment where I give these concluding remarks. And Lenore, in her infinite wisdom, advised me to write presenter notes. So this is the first time I have really spelled out my whole speech in the presenter's comments. And I was thinking that in the worst case, somebody else can read them. But for now, I'm fine. Okay. So first of all, let me thank you. So the 4 organizers, where are they? Well, actually, Andre could not come. So I want to thank Daniel, Andre, Martin, and Thomas for organizing this event. It came really as a big surprise. At first I hated the idea, but then I realized that I really appreciate the effort. And I also thank the speakers of today. It was a wonderful session, and I thank all the people who came to this workshop, some from far away, and so thank you, and and I hate you all for doing this to me. So. So we talked a lot about the past. And so I will retire as a teacher in 2.5 years, but I will not retire as a researcher. And so I want to expose to you the plan of what I will do in the next 65 years. And actually, I don't know what I will do in the next, I even don't know what I will do in 1 year from now. So I can talk to you about my obsessions of the moment, right? And I will talk only about 2 of those. So software model checking for concurrent programs. So we started with software model checking for sequential programs, first for safety. And since we couldn't do safety, we made it more difficult. We went to termination, right? And since we can't do sequential programs, let's go to concurrent programs. Always, if you can't solve a problem, try the next harder problem. And so actually, it may be that some things may be easier for concurrent programs. Perhaps it may be easier to find the right assertions. And then what we have to deal with is, well, the problem of state explosion, right? So now by state, I mean simply the nodes in the control flow graph of the concurrent program, sometimes called the product graph. And the number of nodes grows exponentially in the number of heads, in the number of threads. And so then there is the next thing that you need to go through the paths of this product graph, and that is worse. So what really kills us, and this is what we noticed in the experiments when Rupak and Jochen, we started to work on ticket algorithm, it's the non-determinism. And it's unbelievable. So you can do tickets for, you can prove the algorithm for 2, 3, 4, and then suddenly for 5 it stops, right? You cannot. And it was really this non-determinism that comes through the scheduler of for the threads, right? So what are the 2 attacks? And I haven't worked on either for a long time, and then suddenly I'm into it. So the one is partial order reduction. So the idea is we reduce the program to a deterministic subprogram, and this subprogram contains a small selection of program traces and a selection of those that are sufficient to cover all the other ones. So we mentioned before the traces, the equivalence classes, and so you just pick one representative of each equivalence class, prove the correctness for all the representatives, and then you are done, right? So this is one, and the other one is parameterized verification, right? So just give a proof for every number of threads, And this obviously gets rid of the state explosion, right? If you go to the infinite, you cannot go any further, and this is one bold way to address it. And so what I'm obsessed with right now is to combine the two. And when I say combine the two, then I mean, well, we deal with parameterized programs by applying a certain kind of abstraction that Baruch Abdullah calls view abstraction. In our paper, we called it Cartesian abstraction. And it accounts for the fact that when you look only at a limited number of threads, but then with this abstraction, you account for the fact that there may be always some other thread who is still in one of the states that a thread has encountered before. And so now the question is, how do you proceed? Do you first apply the Cartesian abstraction and then you reduce, right? So if you first go to a larger subset and then you go to a smaller subset, or do you go first to the smallest subset and then you abstract and you go to the larger subtract, to the larger set? And this, I find this intriguing, right? If you go first to a subset and then to a superset, where are you? But the hope is that you do it in a systematic way and that you get something out of it. Okay, so this is one of the two obsessions I wanted to talk about, the combination of partial order reduction and parameterized verification. And then the next one is requirements. So I always thought requirements is so boring, right? I mean, are there any interesting questions? And I thought this is only for people who want to stop thinking. And this is referring to something that, can I tell the story? Yeah, so Rupa got this as feedback when he told Martin Reinhardt that he wants to work on testing. And Martin Reinhardt said, maybe you just want to stop thinking. And I feel a little bit like this. And obviously requirements are important, but this is not enough as a motivation, right? I mean, yes, we have these two inputs, the system and the correctness criteria, and we have to get the correctness criteria from somewhere, and from where do we get them? And yeah, so people spend a lot of time writing requirements, and they spend a lot of effort, but these requirements are in natural language. And so it feels like you write them, but you never use them, right? Because it's not a beautiful natural language, and it's very hard to read them. So what can you do with them? So one thing you can do is to transform them into formal requirements. And this is why I asked the question to Shankar, right? Extract logic from natural language. And the engineers at Bosch and Mercedes, they do not write formal requirements. I mean, they don't have the mindset for that. They don't have the patience. You need to be kind of autistic to write formal requirements. And this is how computer scientists come in, right? And so what we look at now is what if we, without the domain knowledge of Bosch and Mercedes, we take the requirements in natural language from Bosch and Mercedes, and we write formal requirements. And since we don't have the domain knowledge, the formal requirements, they reflect only part of the meaning. But still, the question is, what can you do with these formal requirements? So can you use them for monitors? Can you use them for test generation? And can you use them to detect errors in the requirements? So can you check certain properties? And then there is a certain question. So these properties of the requirements, they are correctness requirements for correctness requirements, right? Because requirements are correctness properties. Sorry, this is what I have to say. So I kind of like this, who is the guardian of the guardian, right? And this you can go on forever. Okay, and so I I want to finish by something more serious. So an homage to three persons who are no longer with us and who played a big role for me as a mentor and a role model. So Maurice Nivard was my PhD advisor, and for the better or for the worse, I adopted his style of advising PhD students. And that's essentially trust them and leave them alone, don't disturb them in their creativity. And I heard a complaint that, well, not all of my PhD students appreciated this kind of supervision. Then Harald Ganzinger, he was my group leader at the Max Planck Institute, and he was his principle for guiding the member of the group was similar, right? So he told them, this is your chance, take it or leave it, right? So trust, no control, and no breathing into the neck. And then Amir Pnoeli, I mean, excuse me? Okay. So Amir Pnoeli, he was great scientist and a great sense of humor. I remember so many jokes he made. And I'm extremely grateful because he was one of the first people who understood the interest of transition invariance. And he encouraged Andre and me and then Byron to really go on this. So I started by thanking you, and let me just repeat you. Thank you very much.
I guess we can also make room for questions to you if somebody has a question for you.
You sounded like termination for software is a solved problem. But this is...
What I said is we could not solve it.
Okay, I see. So I just wanted to mention that for termination we have not even witnesses, right? So in a couple of years ago we were saying that, okay, verifiers that spit out yes or no have no value, they are useless, unless they tell us justification why the answer is yes or no. And for termination, we are still having the situation from 10 years ago or even more, where we have an answer yes or no, but we need witnesses. Yeah. So let's work on this.
So we heard several talks about reducing termination or liveness to safety, and the approaches were very different, right? So transition invariance, what Lenore did, what Jochen presented. So it will be an interesting problems, yeah, to come up with witnesses that are produced by one tool and that then are validated by another one. Yeah.
We also generated ranking.
Yeah, yeah. So. So Rupak's suggestion is run the program and see where it terminates.
Do we have one more question for Andreas? If not, then like.
Can you remind us what the meaning of life paper was about? Because I never actually went and read it. I just saw the title.
So the title of the paper, so there is one version which is the meaning of life, but then we realized that we were a little bit presumptuous and it was then called Towards the Meaning of Life. And life was a programming language, and life stands for logic, inheritance, functions, and equations. So just put everything into it, right? And yeah, that was in a former life when I was at DEC PRL. So most people even don't know what DEC is, right?
Did you have a follow-up with the Holy Grail?
No, not really. Yeah.
If there's nothing else, then thank you again, Andreas.